Welcome to Pi Art Tuition, a series of mini tutorials to help you get more out of your creativity when drawing and painting. In this third video, we're going to have our final look at primary colours. If you haven't had a chance to watch the previous two videos on this subject, I strongly recommend that you do so. In the previous two videos, we looked at what are the three usual primary colours? What actually is a primary colour? Why are there two different sets of primary colours? What exactly is the second set of primary colours? In this video, we'll be explaining how do the pure hues of the rainbow produce the millions of different colours we see around us? When mixing two primary colours to give a third colour, is it our eyes or our brain which generates the third colour? Does the colour magenta exist in reality? How was magenta discovered, and how did it get its name? So first, how do the pure hues of the rainbow produce the millions of different colours we see around us? Just to recap, the first set of primary colours we discussed relates to light reflected off a coloured object, for example, the pigment in your paint. White light from the sun contains all the colours of the rainbow. These pure colours of the rainbow are reflected off different objects in different ways. Different pigments reflect different colours. The yellow pigment, for example, absorbs all the colours except yellow, which it reflects. Blue pigment, on the other hand, absorbs all the colours except blue, which it reflects. Each colour of pigment absorbs all the colours except its own colour, which it reflects. This is how we see most of the objects around us, by reflected light. The pure colours of the rainbow contained in white sunlight are absorbed and reflected in different proportions to give us all the colours we see. This process is called a subtractive colour model because each pigment absorbs many colours in the white light and reflects only certain colours. The pigment takes away colour from the white light, that is, the colours of the rainbow, which is illuminating it. Now, you may have already thought of a flaw in that explanation. There's something missing. The objects in the world around us aren't just in pure colours of the rainbow. The world would look really strange if this were the case. In fact, the rainbow colours contained in white light combine in various proportions and in various intensities to form millions of different shades, tints and tones when reflected off objects. That's how we see all the different colours around us. For example, if we start with the pure colours of the rainbow, which scientists and artists call hues, we can create lighter versions of these colours either by illuminating the object in stronger light, or, if we're creating a painting, by adding more white pigment into the mix of paint. The resulting colours are known as tints of the original hues of the rainbow. Similarly, shades of the original hues of the rainbow can be created either by reducing the amount of light falling on an object, or, if we are creating a painting, by adding black pigment to our mix of paint. We can even reduce the amount of colour itself. In other words, we can desaturate the colour to produce so-called tones of the original hues. This happens when the object is illuminated by a combination of hues because of light reflected off other objects. In other words, it's no longer illuminated by the hues of the spectrum in equal proportion. It can also happen when the object contains various pigments mixed together. In painting, the easiest way to desaturate a pure hue is to add grey in increasing amounts. Our next question was, when mixing two primary colours to give a third colour, is it our eyes or our brain which generates the third colour? Remember, a pigment takes away colours or hues from the white light which is illuminating it. Most hues are absorbed, and one or more hues are reflected. The reflected hues give the object the colour we observe. Let's have a closer look. Again, most hues are absorbed by the pigment or pigments of the object, and one or more hues are reflected by the pigment and detected by our eyes. But you'll have no doubt noticed that we can create a new colour by simply mixing two existing colours together. Imagine we have just mixed magenta and cyan pigments together. The reflected magenta and cyan light will be detected by our eyes. If the pigments are well mixed, and there are no large areas of unmixed magenta and cyan pigment, the light reaching our eyes will be a mixture of the two wavelengths of light. One wavelength will belong to the magenta light, and the other wavelength will belong to the cyan light. The cones, that is the sensors in our retinas, will respond to both wavelengths of light and send a message to our brains, which is an average of both. In other words, we will see blue light, which is halfway between magenta and cyan on the visible spectrum. Please note, technically, the colour magenta isn't actually part of the spectrum. It's not a colour of the rainbow. But I'll be talking more about that later. Let's prove that combining magenta and cyan wavelengths produces an apparent blue wavelength of light in our eyes. Let's take a sample of these two primary colours, cyan and magenta. And now let's populate the screen with these two colours. Let's make the pattern of squares smaller. And smaller. And smaller still. And smaller still. And even smaller. And so let's compare the final colour with the two original colours. Hopefully you can see very clearly that the resulting pattern looks blue, albeit a pale blue. The colour is pale because we're looking at a screen which emits light. This demonstration isn't perfect. If we did the demonstration using patterns of coloured ink printed on paper, then the blue would be a lot darker. Let's show this result in a different way. Here we have an area of the screen coloured magenta. And here's another area, this time coloured cyan. At first glance, we might find it hard to believe that, provided the areas of colour are small enough, our eyes will combine the wavelengths of magenta and cyan to produce an average of both, namely blue, or pale blue in this case. This pale blue area is just for comparison to show the type of colour we will see if we combine magenta and cyan. I'll now fill in the empty area in the top half of the screen with small squares of magenta and cyan. If the area of squares of magenta and cyan occupies a small enough area in our retina, our eyes average out the wavelengths of the two colours to produce the wavelength of blue, or pale blue in this case. Try the following experiment. View this screen in a darkened room if you can. If you're viewing it on your smartphone, hold the phone at arm's length. If you're viewing it on a computer screen or a smart TV, try walking a short distance away, say 6 or 9 feet or 2 to 3 meters. The area of small squares should also turn pale blue and look very similar to the area of solid pale blue below it, which I placed there for comparison. OK, let's try a different set of colours. This time we'll try small squares of magenta and yellow. Here's magenta, and here's yellow. And here's an approximation of the resulting colour if we mix both colours together in a small area, so our eyes can't distinguish the squares. Again, if you hold your smartphone at arm's length or walk a short distance from your computer or TV screen, the small magenta and yellow squares should merge to form a pale red colour, similar to the comparison colour in the lower half of the screen. If that weren't enough to convince you, let's try small squares of cyan and yellow this time. Here's a large area of cyan, and here's a large area of yellow. And here's a representation of the colour we will see if we merge the two colours together, a pale green. As before, hold your smartphone at arm's length or walk a short distance from your computer or TV screen. The cyan and yellow squares should merge to form a pale green colour. This cyan and yellow demonstration works particularly well on screens. Try bringing your smartphone screen close to your eyes and then holding it away at arm's length and then close again, repeatedly. Or move close to your computer or TV screen and then move away and then close again, repeatedly. I think you'll agree it's quite impressive how the area of small squares changes from discrete squares of cyan and yellow to an area of uniform pale green as the screen moves further from your eyes. So, regarding the question, when mixing two primary colours to give a third colour, is it our eyes or our brain which generates the third colour? Well, the answer is both, actually. Let's see how this actually works in more detail. There are two types of cells in the retina at the back of the eye. The rod cells are sensitive to light of low intensity, such as at night or in a darkened room. They don't differentiate colours, so the image we see is a kind of black and white image. The other type of cells are cone cells. These are in three categories. Some cone cells are mainly sensitive to the wavelength of red light. Other cone cells are mainly sensitive to the wavelength of green light, and others are mainly sensitive to the wavelength of blue light. If we think about all the colours of the rainbow, known as hues, we may think that our eyes see all the colours with the same sensitivity. In other words, we may think that the cone cells in our retina are equally stimulated by red, yellow, green, cyan, blue, and violet light. But that's not the case. Specific cone cells are sensitive mainly to red light, others to green light, and others to blue light. The cone cells are distributed over the surface of our retina, so we get an even colour image over the retina. Imagine we were looking at a colour which stimulated the red cones of our retina by 30% of their full stimulation, and which stimulated the green cones by 60% of their full stimulation, and stimulated the blue cones also by 60%. Our brain uses the amount of stimulation in each of the types of cones, red, green and blue, to calculate what the actual colour of the object is. In this case, the colour is teal. If the object is large, and the area of colour occupies a large area of our retina, then different sets of cones detect the wavelengths of light of each of the areas of colour. We see distinct shapes. For example, distinct magenta and cyan squares. One area of cones detects the wavelength of light from this magenta square. Another area of cones detects the wavelength of light from this cyan square. But if the object is small and the area of colour occupies an area of only one set of cones in our retina, then that set of cones detects a mixture of two or more wavelengths of light. The brain then averages these wavelengths and sees a third, new colour, in this case blue. In the case we've just seen, the cyan and magenta or cyan and violet squares were so small that each set of cones in the eye received two wavelengths of light, cyan and magenta or violet. Our brain averages these two wavelengths and creates an intermediate colour, blue. So when mixing two primary colours of pigments, for example paint, ink, dye, etc., to give a third colour, the cones in our eyes are stimulated by two different colour wavelengths. White light, which contains all the colours of the rainbow, illuminates the object. Our eyes detect the two different wavelengths of light coming from the mixture. Our brain analyses these two wavelengths and combines them to create the same colour as would be generated by simply viewing that third colour. So magenta and cyan, when mixed together, becomes blue. And now for the strange case of the colour magenta. Does it exist in reality? This is the real spectrum of colours in white light. And here's a common graphical representation of the spectrum. There's no magenta in the real spectrum. It's artificially added to the graphical representations of the spectrum. Mixing any two hues of light on the spectrum creates another hue which is also part of the spectrum. Yellow and cyan on the spectrum give green on the spectrum. Similarly, red and yellow on the spectrum create orange on the spectrum. So if we take yellow pigment and cyan pigment and mix the pigments together into small enough particles, we get green. The wavelengths of the two hues on the spectrum are averaged by the brain to create the third hue, also part of the spectrum. Similarly, if we take red pigment and yellow pigment and mix the pigments together into small enough particles, we see orange. Again, the wavelengths of the two hues on the spectrum are averaged by the brain to create the third hue, also part of the spectrum. However, if we take red and blue, the wavelengths of these colours is averaged by the brain to create magenta, which is not part of the spectrum. The average of the wavelengths of red and blue are a type of yellow-green colour. But the cones in our eyes aren't detecting the wavelength of green at all, so our brain compensates by the clever trick of presenting us with a made-up colour that doesn't have its own wavelength and is not on the visible spectrum at all. Some people suggest that the natural position of magenta is somewhere near violet on the spectrum, which is why graphical representations often squeeze it in that position. Whereas actually, the wavelength of magenta is similar to that of green. Nevertheless, people tend to associate magenta with the violet end of the spectrum. So let's recap. The rainbow colours of white light, which we call hues, combine in various proportions and in various intensities to form millions of shades, tints and tones when reflected off objects. And it's these shades, tints and tones which make all the objects in the world around us appear as they do. Pure hues of the rainbow and shades, tints and tones of those hues create combinations of wavelengths. This means that we can all see millions of different colours with subtle differences between them all. If there were only the pure hues of the rainbow, and every colour we saw was a single wavelength from the spectrum, the world would appear very strange indeed. Thankfully, we do have shades, tints and tones which create such a diverse and interesting visual landscape for us. So, let's summarise. Does the colour magenta exist in reality? No, it's created in our brains when we see a mixture of red and blue light of certain wavelengths. Now this in itself isn't unusual. Most colours we see are created in our brains when we see combinations of different wavelengths, and the brain takes an average of these wavelengths to create the final colour, a hue, a shade, a tint or a tone. The difference with magenta is that the average wavelength of red and blue is a yellow-green colour, not a violet colour like magenta. But is magenta really a primary colour? Yes, regarding pigments, paints, inks and dyes, magenta, yellow and cyan are the primary colours. Now you may remember, if you watched the first video in this series, that one definition of a primary colour is it cannot be created by mixing any other colours. But magenta is created by mixing two colours, red and blue, and possibly white as well. The fact that magenta is a primary colour and yet can be created by mixing other colours is just a strange phenomenon which scientists and artists can debate about. We won't get into that debate here. The point is, magenta can either be created by using a substance which naturally reflects both red and blue combined, such as the fuchsia flower, or by mixing two pigments together. Just a little bit of history. The fuchsia flower was discovered and named in 1696 after a German botanist called Leonhard Fuchs, who lived in the 1500s. Technically, the flower should be pronounced fuchsia, but we English speakers here in the UK are notoriously bad at pronouncing foreign words. By the way, the letters CH in German are pronounced like the Scots pronounce Loch, as in Loch Lomond. People were able to obtain magenta dye from the fuchsia flower. The dye itself emits two wavelengths of light, one at the red end of the spectrum and the other at the blue end. In 1856, an aniline dye called rose aniline hydrochloride was created. It was also known as fuchsine, named after the flower. But 3 years later, fuchsine was renamed after a town on the outskirts of present-day Milan in Italy, in which a battle took place. The town is called Magenta. Nowadays, if we want to create a magenta-coloured pigment which is close to the original magenta dye, we can mix red, blue and white pigments together. We can also create magenta with light-emitting devices such as the computer or TV or smartphone screen that you're watching at the moment. If we look closely at the pixels which create the image on the screen, we can see they are made up of red and blue segments. This was covered in detail in the previous video. So in conclusion, what have we learned about the primary colours of pigments? The primary colours of pigments, including paints, dyes and inks, are magenta, yellow and cyan. If we spread yellow ink onto paper, the ink absorbs all the colours of the rainbow contained in white light except yellow, which it reflects. Similarly, magenta ink absorbs all the colours of the rainbow contained in white light except magenta, which it reflects. Remember, magenta ink actually reflects two wavelengths of light, red and blue, but don't get confused by that. Let's just say magenta reflects magenta coloured light and leave it at that. Also, notice that when magenta and yellow ink are mixed together, they produce the colour red. Cyan absorbs all the colours of the rainbow except cyan, which it reflects. When mixed with yellow ink, cyan creates green, and when mixed with magenta ink, cyan creates blue. Notice that when all three primary colours are mixed together, magenta, yellow and cyan, they create a dark blue or a dark brown colour, depending on the exact hue of the pigments. This is why printers use black ink as well as magenta, yellow and cyan to create colour prints with a full range of contrast. The black ink reflects hardly any light, and therefore the black reflection is represented here with a dotted line. There's no such thing as black light as such. Now we've been discussing coloured inks here, which are semi-transparent. Please note that when mixing paints, because they're much more opaque, the process is not as successful in producing second and third colours. The resulting colours tend to be a lot duller. Okay, now we know what the primary colours of pigments are, that is, of paints, dyes and inks. So what? How does that help us to produce our artwork? We can gain an appreciation of how to mix coloured pigments to accurately produce any colour we want. Well, that rounds up our study of primary colours. If you haven't managed to look at the first two videos on primary colours on this channel, I strongly recommend you do so. In subsequent videos, we'll be looking at how to produce full colour ink drawings and paintings using just 3 primary colours of ink. We'll learn how to mix the 3 colours of ink in various proportions to produce blue, green, red, purple, teal, brown, burgundy, orange and sap green. We'll learn how to mix coloured paints and inks accurately in order to produce any colour we want, and match colours to existing colours in a scene in front of us or on a photo that we're working from. We'll be looking more into what lots of the art jargon words mean, such as tone, tint, hue, intensity, cool colours, warm colours, shade and value. We'll find out how to draw and paint shiny things, how to draw and paint a portrait and make sure we get all the proportions of the face right, how to draw and paint hair and not falling into the trap of drawing lots of parallel lines. And we'll be looking in detail at perspective. How do vanishing points help us in our art? What's the difference between a wide angle of view close to an object and a narrow angle of view a long way from the object? How do we draw or paint objects and shapes which repeat and recede into the distance, such as the arches of a bridge? These and many more groundbreaking topics will be discussed in the next thrilling instalment of Pi Art Tuition.